The only other thing that I wanted to talk about with regard to gated channels, besides your voltage gated, your mechanically gated, and your chemically or ligand gated channels, we have these leakage channels. And leakage channels are channels that are specific to one ion but may let other ions through under certain conditions and will open randomly to allow ions to go through. And typically what you'll see in a resting membrane is potassium leakage channels that allow potassium to constantly leak out of the cell into the extracellular space, thus giving more positive charges on the outside, contributing to that potential difference between the outside of the cell being positive and the inside of the cell being negative. So leakage channels are important in helping to maintain potential differences across the membrane, along with the actions of the sodium-potassium pumps that are constantly working as well. Now, equilibrium potential is a concept that many people have difficulty with, but basically it's defined as the membrane potential in millivolts, where the net flow of a particular ion, you could be talking about sodium, potassium, calcium, down its concentration gradient is 0. So no flow of that particular ion, the millivolt at which no flow of that particular ion occurs. And so if that's to be true, then the chemical and electrical forces, in other words, the chemical gradient and the electrical gradient, are balanced across the membrane. If you go to Canvas and you check out the video that I put underneath the nervous system crash course lectures called Equilibrium Potential, you'll find a video that not only explains membrane potential and equilibrium potential and how they relate to each other, but what the importance of equilibrium potential is to the potential of the membrane. So finally, a little explanation on how voltage gated channels specifically work. In resting conditions, here it says minus 90 millivolts, but it could just as easily be minus 70 depending on what part of the nervous system you're talking about. You notice that the activation gate is closed. All right, so no sodium can get in. But when the membrane in that area reaches threshold potential, minus 55, the activation gate opens and sodium is allowed to go through. And so as sodium's going through, bringing more positive charges into the cell, that minus 55 voltage is going to change to a plus 30. Here it says plus 35, but again, relative terms. And when the membrane potential reaches plus 30, then the activation gate doesn't close, but the inactivation gate closes. And during the time that this inactivation gate is closed, what's going on is no more sodium is going through, and therefore you prevent the backwards propagation of an action potential. So this inactivation gate helps keep the action potential moving only in one direction. At the same time that this inactivation gate is closed, what's happening is that your sodium-potassium pumps elsewhere in the membrane are pumping sodium back out and potassium back in, taking your overshot minus 90 millivolts, your hyperpolarized cell, back to resting of minus 70. And once the cell reaches back to minus 70, this activation gate is going to close and the inactivation gate is going to reopen. Sodium will still not be allowed through because you have not sent the signal to open that activation gate yet. But as soon as the membrane around this channel depolarizes again to threshold, that activation gate will open and you're able to propagate another action potential.